Okay, so I wanted to expand what I wanted to expand upon what I had you do for your homework problem with the conical pendulum. And as a reminder, that's the one where you've got something on string and it is going around, for example, a pole. And so it's making a circular motion, but it's doing that by swinging around. And so this would be our front view. And if we were to look at a top view, we would have the axis in the middle, and then we'd have the circle around it. And then we'd have our, in this context, a ride on it. And let's say that we're going this way. And so in this picture, the cart is coming out towards us. The ride is coming out towards us right there. So if we were to draw the acceleration vector, we know that the acceleration vector is going to point towards the center of the circle. I should specify that this is a constant angular speed that we're looking at right now. So the speed in meters per second is also a constant, but the velocity is continually changing directions. So the acceleration is always towards the center of a circle, which means that the acceleration is pointing this way from our ride, towards the center of the circular path that it's creating. So in the problem, I gave you a theta, and I gave you a length of this rope, and I asked you to find the tension in this rope. I also gave you a mass for the ride. So the question I asked so far was to find the tension. And so if we draw a free body diagram for this, we find that, of course, we have weight, which is pointing straight downward, and our tension is pointing at an angle. Well, if the acceleration is pointing exactly to the right, then that means F net needs to be pointing exactly to the right, which means the vertical number of boxes up and down need to cancel out. So this net force is going to be due to the x component of the tension. So here we have the tension vector, and if we look at the angles in these triangles, we see that this is the angle theta, and if you really want, this is also the angle theta. And I will let you do some geometry to figure that out for yourself, but the idea here is that there are two components. There's the y component of the tension, and there is the x component of the tension. The hypotenuse is the tension. And so sine theta is the opposite, which is tx, over the hypotenuse, which is the magnitude t. So if we want tx, we have t times sine theta. There's one more geometric thing we need to do, and that is to figure out the radius of the circle, because this is the length of the chain, and this is the angle that the chain makes. So what is the actual radius of the circular path that it's making? Well, let me redraw this picture a little bit. So here is, it's not an arrow though, because this is the chain. This is not the tension vector. That is an easy thing to confuse because the tension vector is going to point along the chain, but this is real life meters that we're talking about, length of the chain. And so the radius of the circle is essentially the x part of the triangle that you get when you put the chain along the hypotenuse. So the radius is equal to the length of the chain times sine theta. I'm also going to add the y component to our tension. And of course, if the x component is sine, then the y component is going to be cosine. You can look at the geometry and get that. Okay, so we're going to write Newton's second law in the x direction and in the y direction. In the x direction, the only force is the x component. And the acceleration, remember, anytime we have uniform circular motion, if we have circular motion at a constant speed, then that tells us that the radial acceleration is going to be v squared over r, or, if we prefer, omega squared times r. We're going to use v squared over r for this. And in the y direction, we have that ty minus weight is equal to m ay. But ay is 0, right? Because as the ride is going around in a circle, it is not moving up or down, so the y coordinate remains a constant, which means the y velocity is a constant of 0, and therefore the y acceleration is 0. If we plug in our equation here, we've got t times cosine theta minus mg is equal to 0. And so we get that the magnitude of the tension is just mg over cosine theta. In the problem, I gave you some numbers. I'm not going to look them up. That's what you need. So that answers the question that I asked. I now am going to ask another question. What is the speed of the ride? Right, so I'm looking for v here. Well, we've actually gotten most of the way there now, because we know that the speed is going to be in this x equation. And so we can just rewrite the x equation down here. Tx is t sine theta, m v squared over r. And we'll put some things in here. We know that t is mg over cosine theta. So mg over cosine theta. We still have our sine theta. We'll see that the masses cancel out. We've got our v squared. And remember that we have an expression for r, which is L sine theta. So like we said, the masses cancel out. And you can decide how you want to simplify this. But v squared equals L sine squared theta over cosine theta. And so v is just the square root of that. Times g. I knew something was wrong here. Okay. G. There we go. GL sine squared theta over cosine theta. Okay. So the second part I didn't ask you in the homework problem, but it is something I want you to know how to do, and you might, I don't know, maybe need to do in the next week or so.